Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of tearing down the black box. In this page, we will cover the transition from the legacy 1957 perceptron architecture to the cutting-edge 2024 Kolmogorov Arnold engine. For nearly 7 decades, the foundation of artificial intelligence has remained remarkably static, relying on a rigid mechanical foundation that has served us well, but is beginning to show its age. Today, we are putting that 68-year-old foundation on the workbench and unboxing its potential replacement. We will explore how traditional neural networks often act as data choke points with fixed node densities that create significant bottlenecks. In contrast, the modern Kolmogorov Arnold Network, or KAN, offers an organic and adaptive assembly. This new approach uses adaptive activation paths and dynamic node integration to move beyond the limitations of legacy models. By the end of this journey, you will understand why we are moving from rigid structures toward more fluid and expressive mathematical frameworks that promise to revolutionize how we build and understand machine learning models. Moving into the legacy architecture, we must address the multi-layer perceptron. Every modern artificial intelligence, from the powerful GPT-4 to the revolutionary AlphaFold, actually runs on a direct descendant of Frank Rosenblatt's original 1957 perceptron. When we look at this architecture, we see a structured input layer followed by multiple hidden layers leading to an output layer. In this system, the nodes are considered the active components while the edges are static. This creates what we often call the mathematical hairball, a dense and tangled web of connections that becomes increasingly difficult to interpret as the model grows. While this architecture scales beautifully and has led to incredible breakthroughs, it remains essentially a brute force approach. We can observe what the model thinks by looking at its outputs, but we have almost no idea how it actually arrives at those conclusions. The complexity of the connections inside the hairball masks the underlying logic, leaving us with a powerful tool that remains fundamentally mysterious in its internal operations. Let's zoom in on the edges of a multi-layer perceptron, which we might call the dumb multipliers. In a standard MLP, an edge does exactly one thing and one thing only. It takes an incoming signal and multiplies it by a static scalar number, such as multiplying x by -2.3. This leads us directly into what we call the black box trap. When you train a massive model with 1 billion parameters, what you actually end up with is 1 billion disconnected numbers. These numbers represent the weights of the connections, but they do not convey any intuitive meaning or physical understanding. You simply cannot extract physical laws or deep insights from a 50-kilogram block of melted metal, which is a metaphor for the dense and unreadable nature of these weight matrices. While these multipliers allow for massive scale, they lack the expressiveness needed to truly explain the relationship between data points. We are essentially forcing the model to learn through sheer repetition and volume rather than through meaningful functional representations. Next, we turn our attention to the nodes within these legacy networks, which function as rigid gates. In the MLP paradigm, all nonlinear computation is forced into the node itself. The process is straightforward but limited. The node simply sums up all the incoming signals that have already been multiplied by the edges and then squashes that sum through a fixed function like sigmoid or ray-LU. For example, a ray-LU gate might simply say that if the input is less than 0, the output is 0, but if the input is greater than 0, the output equals the input. This creates a rigid mathematical toll booth where the intelligence is essentially trapped in the switch rather than the wire. We are forcing complex and multi-dimensional problems through these narrow bottlenecks, which limits the flexibility of the model. By relying on these fixed mathematical gates, we restrict the ways in which the network can transform and represent information, leading to a system that is functional but lacks the elegance of more dynamic mathematical solutions. To understand the future, we must look at a Cold War ghost from 1957. In that year, Soviet mathematicians Kolmogorov and Arnold proved David Hilbert's 13th problem wrong. They demonstrated a powerful existence proof, showing that any complex and multi-dimensional function can be perfectly represented as a sum of simple one-dimensional continuous functions. This mathematical theorem suggests that we do not necessarily need high-dimensional complexity at every step. Instead, we can break down any complicated system into a series of additive one-dimensional curves. While this theory was mathematically sound and highly significant, it remained a theoretical curiosity for decades. The architectural implementation was possible in theory, but until 2024, no one really knew how to practically engineer it into a working neural network. We knew the architecture was possible, but we lacked the tools and the perspective to move it from a chalkboard equation into a functioning piece of software that could compete with the established perceptron model. This leads us to the Great Reversal and the unboxing of Kolmogorov Arnold Networks, or KANs. This represents an architectural inversion that changes everything by simply swapping the roles of the nodes and the edges. In a traditional MLP, we have active nodes and dumb edges where the intelligence is trapped in the switches. In a KAN, we have dumb nodes and active edges. We have essentially taken the nonlinear math out of the junction boxes and mapped it directly onto the wires themselves. Instead of a signal hitting a rigid gate, it travels along an edge that is itself a complex mathematical function. This shift allows the network to be far more expressive with fewer components. It is a fundamental change in how we think about information flow. By making the connections active rather than the nodes, we allow the network to learn more nuanced relationships without needing the massive, tangled hairballs required by the older perceptron-based models. It simplifies the structure while increasing the power of the individual connections. Let's look closer at these active edges, which are built using learnable B-splines. In a KAN, an edge is not just a single number multiplier. Instead, each edge is a dynamic and morphing mathematical curve defined by an equation involving weights and splines. The AI does not just learn a static weight. It actually learns a specific shape by moving control points during the training process. A standard KAN edge might have about 7 parameters, which is more than a single MLP weight, but every single one of these edges is infinitely more expressive than a static multiplier. As the network trains, these curves shift and bend to fit the data perfectly. This is why we say that in this architecture, the shape is the intelligence. By allowing the edges to take on complex shapes, we give the network the ability to model intricate patterns with much higher precision. The intelligence is distributed along the path of the signal, allowing for a more natural and fluid representation of the underlying data. Because the edges do all the heavy lifting, the nodes in a KAN perform what we call naked summation. By the time the data actually hits a node, every complex and nonlinear transformation has already happened on the edges. This means the node has exactly one job left, which is purely adding the curves together. This is the Kolmogorov Arnold theorem rendered in physical silicon, with one-dimensional curves flowing into simple sums. There is no activation function like ray-LU or sigmoid inside the node because the nonlinearity is already baked into the edges. This setup is not just an approximation of the theorem, it is a direct implementation of it. By removing the complexity from the nodes, we create a much clearer and more transparent architecture. Each part of the process is clearly defined, with the edges handling the feature transformation and the nodes handling the integration. This clarity is a major step forward in creating models that are not only powerful, but also easier to analyze and understand from a mathematical perspective. One of the production superpowers of this new architecture is the ability to prune the math. In a traditional MLP, when a connection is irrelevant, the weight might get microscopically small, but it stays in the network, taking up space and computation. In a KAN, when a connection is determined to be irrelevant to the task, the network physically flattens the spline to a horizontal line representing 0. This means that a flat spline is a clear signal that you can physically rip that connection out of your architecture entirely. This process of multiplication by 0 creates a truly dead connection that can be discarded. This leads to much more efficient and sparse models. Unlike the dense blocks of MLPs where everything is connected to everything else, a pruned KAN becomes a streamlined map of only the necessary relationships. This level of architectural efficiency allows for smaller, faster models that do not sacrifice performance for the sake of simplicity, making them ideal for specialized scientific tasks. Perhaps the most exciting feature is the use of symbolic regression, which positions the AI as a co-scientist. Because each edge in a KAN is a one-dimensional function, we can actually fit human-readable equations to them. If you feed the network planetary data, the architecture can literally output recognizable equations like E equals mc squared. This completely shatters the black box that has haunted AI for years. The AI is no longer just an oracle giving you an unquestionable number that you have to trust blindly. Instead, it becomes a collaborator that can hand you a concrete equation. By converting the learned splines into symbolic math, researchers can discover the underlying laws of physics or biology hidden within their data. This bridge between machine learning and traditional science is a game changer. It transforms the role of AI from a predictive tool into an explanatory one, allowing humans to learn from the model just as much as the model learns from the data. This brings us to the parameter paradox. For smooth and compositional scientific functions, a KAN with just 200 parameters can mathematically match the performance of an MLP with 300,000 parameters. This challenges the long-held belief that bigger is always better in the world of AI. We should not just scale blindly and hope for the best. While MLPs try to approximate curves with thousands of jagged statistical steps, KANs simply draw the exact curve using their spline-based edges. This massive difference in efficiency shows that architecture truly matters more than sheer size. By using a more intelligent design, we can achieve the same or better results with a fraction of the memory and storage requirements. This parameter efficiency is crucial for deploying models on edge devices or for conducting scientific research where every variable needs to be accounted for. It represents a shift from brute force computation toward elegant mathematical representation, proving that a well-designed small model can outperform a massive, poorly structured one. However, we must discuss the matrix engine versus the spline and the challenges we face. Current hardware like GPUs is forged in silicon specifically to efficiently multiply massive grids of static numbers, which is what MLPs require. A standard MLP edge requires only about 2 floating point operations. In contrast, KAN-B splines can require up to 204 floating point operations per edge. This creates a hardware collision because GPUs generally hate recursive branching and the specific types of calculations needed for splines. We currently live in a hardware monoculture where everything is built exclusively for matrices. KANs are mathematically brilliant and highly efficient in terms of parameters, but they have arrived in a world that is not yet optimized for their specific computational needs. This means that while they are powerful, they can be slower to train and run on existing hardware until we develop new chips or better software kernels that can handle the unique demands of spline-based architectures without the overhead. Going deeper under the hood, we see that the real bottleneck is not just about raw compute operations. The challenge with memory stalls is a major factor. B-spline backpropagation requires accumulating values using atomic add operations, which can create massive traffic jams in memory bandwidth. This isn't just a matter of needing more power. It is about how data moves through the system. If you want to deploy KANs effectively today, custom CUDA optimization is absolutely mandatory to get acceptable performance. Solutions like FlashKAT are being developed to bypass these bottlenecks by optimizing how memory is accessed and updated during the training process. Without these specialized optimizations, the benefits of the KAN architecture might be overshadowed by the inefficiencies of running it on hardware meant for something else. This technical hurdle is the main reason why we haven't seen KANs replace MLPs overnight. But it is a challenge that engineers are working hard to solve as the potential benefits become more obvious to the community. We are now in a phase of escaping the local minimum of AI research. For a long time, the entire deep learning revolution has been a series of optimizations within the 1957 perceptron paradigm. We have seen the rise of transformers and state space models like Mamba, but these are still largely built on the same foundational ideas. KANs prove that completely different mathematical foundations exist and are viable. The monoculture of traditional neural networks is finally cracking. We are entering a sort of Cambrian explosion of digital architectures where the perfect design hasn't been built yet. By exploring alternatives like KANs, we are pushing the boundaries of what is possible and moving away from the safety of the established local minimum. This diversity in architecture is essential for progress. It allows us to match the right tool to the right problem, rather than trying to force every challenge through a single type of model. The future of AI will likely involve a mix of these different approaches, each excelling in its own domain. The final takeaway is that you must choose your engine wisely based on your specific needs. It is important to realize that pure KANs will likely not replace MLPs for scaling trillion-token language models in the immediate future. MLPs remain the sledgehammer of the AI world, perfect for the massive scale required for language and vision tasks. On the other hand, KANs represent the scalpel, an ideal tool for science and discovery where precision and interpretability are paramount. They will likely revolutionize how we discover the laws of physics and analyze complex scientific data. You should always strive to understand the limits of your hardware, but you must never let those limits dictate your imagination or restrict the types of architectures you are willing to explore. As we close this session, remember that the tools we use shape the way we see the world. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.